Hey guys, so as a part of a personal effort to improve my knowledge of the EVM, I've decided to make this video series on this extremely popular EVM puzzles repository. So it contains basically 10 puzzles which you need to solve. So it basically provides you with a certain bytecode, and you need to input some call data and message value, and you need to reach a certain state. This video and subsequent videos are intended for people who already know something about Solidity, already have some kind of at least basic knowledge on the EVM, and also I've added this third point. When you're dealing with low level stuff, it's very important to have in mind these conversions between different number formats. So basically between decimal and hex and binary. It's much easier to work with if you can think on your feet. So when someone tells you 4-byte selector, you immediately know that this is like eight digits in hexadecimal. So basically that one byte is equal to 2 hex. I won't go into details on how to start this repository or anything else. It's already described here in the README. I will just actually be using this EVM codes webpage. So this contains the reference to all of the opcodes. And it also contains this playground in which you can input any type of bytecode. Then you can input some call data and some value, and then you can check what's the execution flow through this bytecode. Since each opcode is actually two digits, and when we are going to be solving these puzzles, we are going to be going through the description of each opcode, and we'll go in details how it works. So let's go to the first puzzle. So each puzzle is structured in a way that you have a certain piece of code. We're going to paste that to the playground, and it specifies: are you supposed to provide the value, and are you supposed to provide the data? Some of them require just the value or just the data. Some of the puzzles require both value and data. For the first puzzle, we just need the value. So as I said, when you let's just step a bit back. Let's say you've written a smart contract inside the Solidity programming language. You compile it. So the compiler actually, when it compiles it, it actually constructs these. Let me just copy and paste this. It actually compiles it into a bytecode, which is a set of these opcodes. These are basically machine instructions. And then what you would do is you would send a transaction with the whole code, which consists like the init code and the runtime code. So you want to deploy this code into the blockchain so you can later on interact with this piece of code. So this bytecode here, this is equivalent to let's say any smart contract which has been obviously compiled to bytecode and deployed on the blockchain. So it's just a set of instructions. And the EVM, during the execution, it operates in different areas. So you have the memory area, you have the stack area, and you have the storage area. I'll just briefly go through each of these. So memory area, let's say you have a function which constructs a certain array, and then it pushes some values onto that array, fills the array with certain values, then removes some values. inside the array, all of that will be stored in memory. So memory is something which is temporary, which is just tied to the execution of a certain function. Stack is the place where you put certain values, you do some kind of a computation on those values, then you might push some values from stack to the memory, or you're going to read some values from memory and then put them onto stack. So there is usually this communication between the memory and the stack, but what's important for memory and the stack, they are just temporary. So they are there when the transaction is being executed on the blockchain. On the other hand, storage is something that is permanent. You probably heard that reading and writing from storage is very expensive. This is intentional because we don't want to bloat the size of the node with too many values that are stored on each contract. So the idea here is to limit people from reading and also writing from storage, since this is temporary. Storage is tied to a specific contract. So each contract has its own storage, and it has some variables which are stored inside that storage. But let's go back to this concrete example. So let's just try. So in this case, we need to input a certain value. Let's just try some random value. This works in a way. So on the right, as I've said, you have a description of these opcodes. You can input value. You can input call data. You press run, and then you can execute through the code. You will see as you execute through the code, you will see how something is added to the stack, something is removed to the stack. You will also see how something is added or removed from memory. And then in the end here, you can have, let's say, the final output, what has happened after the execution. The objective of these puzzles is not to get a revert. So if we step through the code, we first see this instruction call value. It inputs this 2 onto the stack, which kind of matches 2, which would mean, we'll go to the description of each opcode, but based on this, like the first try, I would say that the call value just takes the amount of the value which you passed and puts it onto the stack. Next, we have jump instruction. Then after that, okay, so it's saying that the jump was invalid, that something has happened. I'm just going to like spoil the solution right now here, but here the solution is the following. You're supposed to reach this first jump, and then this first jump is supposed to kind of bypass all of these reverts, jump to this destination, and then after it jumps to this destination, it will just proceed to the stop, and this will halt execution without causing a revert. This is actually just like what? Like 1, 2, 3, 4, 5 different types of opcodes inside this bytecode. It's very straightforward, simple, but we'll just go through each of these. So call value, what I did when I was solving this is I go to the description and check call value. So here, minimum guess is for this puzzle, not something what interests us. Also, here we have the stack input. So for call value doesn't care about the stack. This is what this means. Also, the caller doesn't, you see the opcode above. So the caller doesn't depend on the stack. Origin doesn't depend on the stack, but stack input, but the balance, you see, depends on the stack. However, call value outputs certain thing on the stack. It outputs a certain value. Call value is really straightforward. So call value, when this instruction is reached, it reads the value of the current call in way. In our case, that is 2. And it just outputs that value onto the stack. let's like try. Okay, let's try 10. We run it. Here, A is inputted. Just a side note, this is in decimal. What I said at the beginning, it's good to have these conversions between different number formats. This is in decimal. Here you will see all the values in hexadecimal. So hexadecimal is from 0 to 9 and A to F. So A is actually 10 in hexadecimal. Let's like try 11. Okay, 11 will be B and so on. Let's like try 55. 55 will be 37. So just as a side note, like a quick conversion from hexadecimal to decimal, you take the like this, let's say digit at position 0. You multiply it by 16 to the 0th, so that's like 7, plus 16 to the 1 times 3. So that's 48 plus 7, so it's 55. So what you're doing is 16 to the 0 times the first digit. So in this case, it's like 7. Plus 16 to the 1 times, okay, in this case it was 3. Okay, let's hope this will give. Okay, so it's 55. That's how you have this, how you can have this quick conversion between hexadecimal and decimal. Okay, so now we played a bit with the call value, but we see that also 55 also reverts. Now let's check the jump opcode. Okay, the jump opcode has a longer description, and I invite you to actually, when you're going to be solving these puzzles by yourself, to go in depth into this description. But the bytecode accepts certain stack input. So the value which is on the top of the stack will be taken as a stack input. And what it says is this value counter is the byte offset in the deployed code where execution will continue from. Must be a jump destination instruction. Okay, this sounds, when I was first reading it, it sounded a bit strange. But actually what it's saying is that in this case, 55, jump will read this 37 or 55 in decimal and will try to jump to that position in the bytecode. That like what it's saying, it's byte offset in the deployed code. So the size of this code is from like 0 to 9, it's 10. And this will try to jump to 55. So that's the offset. It's some kind of a position from something. From in this case, it's from the start of the code. And in our case, in order for this to be valid, it needs to jump to this jump destination. This jump destination is at position 8. And it's important to note here that counting starts from 0. So if we input 55, we run it, it's going to revert. If we input 5, again, it's going to revert. So what we need to do is we need to input call value. So when this jump is reached, it reads the call value which was pushed onto the stack, and it needs to jump to this like offset 8, and then after that it will just continue execution to this stop. I think this is pretty straightforward. What's the offset in the deployed code? It's 8. And just take into account we're starting here from 0. This is not 9. It can be a bit confusing. It's actually 8. So we run this 8. We go to the jump. It reads 8 from the stack. And you see, it has jumped to the jump destination. Okay, no, I've pressed this again, but let's try executing again. So we take the call value, jump, it takes 8, it will step into jump destination, and it will stop. So this is the solution to the first puzzle, and in the next video we'll check out the next puzzle.